are two types of the dynamic linking. One is static. Another one is the dynamic. So static means, so for example, in C programs, the standard I/O library has the stdio. So this is the library. So if the .so file, so if this file really physically copy and bind to the a.out file, your file, so this is called the static linking. Okay? It's a linked but it's a static. Fixed physically, the copy and combine into part of the program. What is the benefit?
You save memory.
You waste memory actually. Yeah, so because you have the shared library here, it's shared by other, but when you compile, you can select the static library. But this is your program a.out. But if you select the static linking, this one copied here and attach it to your part of your program. Even though they are linked, but you have another copy, which means
they'll be faster.
Faster. That is the benefit. So that is the only reason. However, if you change the shared library, sometimes the DLL file is changed, like the standard I/O shared file. You need to recompile every time. So it is not recommended. However, when you have really the critical the program, so at that very limitedly you can have the static. Otherwise, it will be shared library, like the .so file, or in Windows is the DLL file. So how do we know the address of the shared library? During the execution. Even not loading, you don't have to know that because you are not going to access the other guy's the SO file, okay, shared file. Instead, when you execute, which means that instruction like the read, not read, is the printf, for example, in C program. So printf or fprintf, they are in this shared library, then you can go to that address and access them. I did one time the static library to build the kernel of database. It's error and many times. Finally, when I compile the kernel with the static library, it's okay. But the problem is, whenever I run the database program, normally the database program, when you connect the database, it requires the several megabytes or the 10 megabytes. But with the static linking, it includes all the shared library for the database. It's 100 to 200 megabyte size, the memory. So it will be, that is the trade-off. Okay, then finally we can using the discuss about the address, so we are able to use the memory. In terms of operating system, we need to allocate the memory based on the address format. So first approach is the contiguous allocation, which means we have the program is a 0 to 100. This is the logical address. Once you load it, it is relocated using the relocate the MMU memory map unit. I forgot the name of this memory management unit. So MMU and the relocatable the register, it will be, for example, the 1000 to the 1100, like this. At this time, we are going to allocate the chunk of them. This is called the contiguous allocation. Old operating system like the MS-DOS use such a contiguous allocation. There are two parts of the memory in contiguous allocation. One is operating system. Another part is the process part. Then the process part will be contiguous. This contiguous can support multitasking, which means the process can be loaded into the memory. Process 1 and process 2, as long as you have chunk of the memory space. So that is the contiguous allocation. At this time, the chunk of the memory is called the partition. Okay. let's see the diagram. So when you allocate the memory, so you need to know the limit and the relocation register. Instead of base, we are going to use a relocation register. So we need to verify from the logical addresses. So we are going to read the memory management unit. Then using the relocation register, which is the same idea of the base, and the limit is the size of the process. We need to check the physical address, whether that is valid. Is it between this one, right? Then the physical address will be, otherwise it will be the error. That is called the trap. Then your program will be stopped. Then if yes, because why we are using such a process, because there's no physical boundary of the memory. So we need to always check the starting and end. And you see the operating system can access the physical memory area. Okay, then how does allocate the partition to the process? So there are different approaches. So basically it will be like this. We can allocate the chunk and another chunk for another process. If process 3 is done, it will be like that. Then we can allocate the chunk to another process like this. However, think about this one. If we have the process like this, so there is a variable space over here, a variable process here. Even though total space is less than the free, but if they are divided, in other words, this is called a whole. If we have a lot of whole, definitely we cannot allocate the chunk for the process. This is called the fragmentation problem. So continuous allocation definitely caused such a fragmentation problem. Okay, so there are different ways to allocate the memory chunk partition to the process. First one is the first fit, second is the best fit, third one is the worst fit. So let me briefly explain, then it's not complicated algorithm, so then we will see the example. First fit is from the lower address, we are going to allocate the first available chunk, free space. First, it's the first available one from the lower address. So that is the first fit. Then second, the best fit is we have a number in the memory. We have the number of partition like this. After we process in and out like this. Then this is a lower address. This is a higher address. Then we are going to find that fit to the process size. In other words, when we allocate the chunk free partition to the process, it generates the smallest, least free space. That is the best fit. The third one, worst fit, is the opposite of the best fit, which means when we allocate the free space to the process, the biggest chunk will be remainder. So that is the worst fit. We cannot say the worst fit is the worst one because it generates the biggest chunk, free chunk. This one is too small to be reused. So we cannot say best fit is the best or worst fit is the worst. So that is just the name. So let's see the example. So here is the memory structure. The lower address, so definitely we have OS, and from 0 to 3000 the memory space. Then so we have H means indicate the whole. So this is a free. So what is the size? It's a 600. And P3 is occupied. Occupy the memory address like this. The H2 is from the 1400 to the 2000. So this is a 600 size. And then P4 is a process. This is a 400. Okay. So using first fit, so we have the new process P1. Which one will be allocated? H1, H2, H3. First,
H1.
H1, because it's from the lower address, this is the first fit. So like this one. then using best fit, which one will be allocated?
H3.
H3, because if I use the H1, so 300 will be free space, right? And if I use the H2, 300 will be the free space. But this one is only 100, least amount of the free chunk. So it's the H3, like this. What about the worst fit? Opposite, either H1 or H2, right? At this time, for the tie-break group, we can use the first fit, so or we can use the other. So either H1, H3 will be allocated for the worst fit. So this is a contiguous allocation. Okay. So obviously, if we are using the contiguous allocation, it causes the fragmentation issue. So even though we have the total free space is how much is that? 600, 600, and the 400. It's a 1600 the free space, right? But if we have the size of 700 the process using contiguous allocation, no way to fit any hole. So this is called the fragmentation. Solution? What will be the solution of such a fragmentation?
Can you separate the process and have it be allocated to different holes?
Yeah, that may be the way, but the contiguous idea of contiguous is anyway we'd like to keep the chunk as a chunk.
Yeah.
So solution is take up. We can move back to the storage like the swap. So we can swap out and swap out and start swap in from the using first fit here, second, and the P2 like this. So this is the compactation, the solution. Obviously, nobody wants to use this one because it's a huge IO. Okay, so that is the fragmentation. Whenever we have encountered the fragmentation issue, even in the file system. So when we see the fragmentation, there are two types of fragmentation. One is, this is called the external, the fragmentation. So external means outside the process. So it's the free space over here, hole and hole. Internal fragmentation is like this. There might be unit to allocate the process. Like if, for example, this is a 712 byte. Our basic smallest unit to allocate is 10 byte. So we need to allocate the 720 byte, even though it's a 712 byte. So at that time, 8 byte will not be used. It's the fragmentation inside the process. This is called the internal fragmentation. Usually, internal fragmentation is smaller than the external fragmentation. Okay, so we will see example of the internal fragmentation later. But this one, the contiguous allocation, causes the external fragmentation solution. Just like the file system, the fragmentation problem, we can use the compactation, which means the backup and the reload takes a long time. Huge IO are needed. So practically, we don't want to use that. So what will be the other solution? Urban already mentioned. Why not? The split or partition the process. At that time, we are not going to partition just in half or the arbitrary the size of the partition. Instead, fix the size. That, for example, if we have the 700 byte, so we are going to chop 100, 100, 100, 100, 100 like this. Then this is the process. This is the physical the memory 0000 and FFFF. Then we are going to chop the physical memory by the same size, 100, 100, 100, 100, 100, 100, like that. Then we are going to allocate this unit by unit. This one will be here, this one will be here, and this one will be here like this. At this time, this unit is called the page. So paging is the fixed size unit of both process and physical memory. That makes sense. If the process and the physical memory, if they are using different unit, it doesn't make sense. So we are going to use the same, the fixed size. Then allocate page by page. It doesn't have to be contiguous. Instead, page by page allocation. At this time, the page is called the page frame. Okay, this is called the page frame. Physical memory is a page frame. Then your process is the logical the page or just the page. So our goal is to allocate this program page or the logical page into the physical page frame. At this time, so this page usually we don't want to use 100 byte the page size, right? Why? Our yes, addressing format is a power of 2. So it should be power of 2, like for example the 2 to the power of the 10 is 1,000. 1,000 is a little bit bigger. So we are using 512 byte as the most of the operating system uses 512 byte as a page size. That makes sense for what? OS block size. What is the typical size of the OS block? 512 byte. When you design the file system also uses the 512 byte as the operating system block, which means I/O is the 512 byte size, 512 byte. So that fit to the memory because eventually we are going to use the memory for the I/O. Do you remember that the class we learned about the direct memory access? So CPU cannot read the data from the hard disk drive. Instead, we need to copy the data into the memory. Then the CPU can read the data. So if we are using the same unit and as the page, that makes sense. We don't want to lose any the fragmentation. So that is the reason the 512 byte is the most popular. However, depending on the operating system and the application use a different size. What are the example of the application that use the much bigger size of this page? Database use much bigger size. Database block. So even the fast response system like this are using 2K, 4K the block size. Big data system use 64 megabyte and 128 megabyte, such a bigger size of the page. Okay, that's great. Then however, this one will be mapped to your program logical, and this is a page frame, the physical. This logical to the physical should be mapped. How can you map this one to this one?
With the MMU.
Similar, it's called the page table. So MMU is called the page table. So where is the page table? It should be in the memory also, same mechanism. Instead of contiguous block, we are using page by page unit. So MMU now used for such a page table. idea of the page table. Do we have the example of the page table over here? Oh, no. So it's okay. So this is the example of the page table. So logical page number. So which means, let's say that this is our program, logical memory. So some of the students confuse, what is the logical memory? Logical memory means it's your program, process. Okay? It's your program, your process. So from the CPU and operating system point of view, your program is nothing but the data in your memory. So eventually, so your operating system the CPU cannot access the data in the file system. So it should be in the memory. So logical memory means it's your program. Then as we discussed before, chart by the page size, page size, page size. And then physical memory. What is a physical memory? Your memory on your computer. So let's say we have the 4K size of memory. Yes, there was a 4K size memory long time before I used. So then, if you are using 512 byte pages, okay, this is a page size. Then, how many pages do you have? Divide by the 512 byte. So it's total 8. So number 0, 1, 2, 7. Total 8 pages. It's a physical. So our goal is math. So how many? So let's say that this is the 2,000 byte. Okay, my program size is a 2,000 byte, 2000 byte. How many page number in this case? How many page number?
About 4.
4, about 4, 3 point something. So we need the entire the page at the last. So even though it need 300, 500 some, the 409 something like that, but still we need the entire whole page. So 0, 1, 2, 3 pages we need. So our goal is to map like this. So logical means it's a program. Your logical page number 0 gonna be physical memory is a frame to the 0, 1. It can be anywhere. It can be anywhere. We will see how to allocate later. It can be anywhere. So page 0. Then how does your computer know? Eventually, your CPU need to access this one, not this one. First, memory management unit, MMU, page table. So check the relative address, then calculate the page number. It's a 0. 0 is in 1. So 1 is, where's 1? You can multiply by the page size. 1 plus 1. This program counter, the relative address. Then you can find the location of the instruction or data. Similarly, page 1 is mapped to the 4, and page 2 is mapped to the 3. Where's the 3? Oh yes, here. And the last page is mapped to the 7. Okay?
Professor?
Yes.
So, but wouldn't we want to also have them in order?
It doesn't have to be in order.
But wouldn't it be beneficial in terms of seek time or no?
That is a good question, but it is better if you locate the crucial part of your program on the process on the lower memory. That is the reason operating system usually decide on lower memory. But it's not huge different. Okay? So because of that, the more problem is if we allocate at the beginning, then but eventually it will be full of because our memory size always typically less than what we need. Entire process cannot be loaded, probably in and out. So we cannot get the benefit of lower memory or the consecutive, the continuous allocation along the number of pages. It will be overhead even to consider.
Yeah, okay.
Mm.
Makes sense.
So this is the memory map, the table unit, and this is the page table. So this is the page table, should be located in your somewhere in your memory as a part of the operating system. And also it should be faster, and CPU should know that. So on your CPU register, you need another register that starting of this one and the end of this one address in your memory on your the register information. So this is the paging example of the paging. So what is the paging? So we don't want the allocate the contiguous, instead we'd like to use the non-continuous, then we can avoid as much the swap in and out possible. Okay, so that is the paging. So idea is we are going to use a fixed size of the block for both logical memory program and physical memory page frame. Okay, then idea is a map between this one to this. Okay. What about this? We can avoid the external fragmentation, definitely, because we chop, then we do not lose the whole or something. What about the internal fragmentation? Do we have internal fragmentation using paging or not?
No, we don't.
No?
Because each, even if we deallocate a process and they're split up, we can map them to different, like the process can be mapped to different.
Yes. That is the external fragmentation. But internal fragmentation means, so here 2000, and where is the 45 byte? It's here, right? So 48 byte is the not needed, but it's inside the page. It's free, but fragmented, but we cannot use it. So this is called the internal fragmentation. So
Okay, so there's fragmentation inside the process.
yes, so we cannot even use, but that's relatively comparing to the external fragmentation on contiguous allocation. It's much smaller, so we can ignore. Even though there is internal fragmentation, but what if you have the 64 megabyte the page size, but you have only 1 byte of data? That happened in the Hadoop system, big data system, 1 byte. So do you need the entire 64 megabyte? So this is an internal fragmentation. At that time, the Hadoop truncate this part. Instead of the page fixed size, the last byte only used as needed in the memory. That is a way to avoid the internal fragmentation in case you are using really big size of the page. However, if you are using 512 byte, it can be ignored. Most of the time we ignore it. So at this time, our address format should be changed, because when you locate the address of location of your the data in the memory, like this. Last time, what we need to do is the offset plus base or the locator, the register. That's it. However, here we need to know first what? Page number. Right? So otherwise we cannot find it. So first, this page number is a page frame number. Then offset inside the page, where is it? Okay, where is it? So there are two parts. When you are using the paging, the address, memory address format is the two parts. Page number and page offset. Question. Here, what is the total size of the disk? P plus D. What is the total size of the address? it depends on what?
Is it 512?
512?
No.
It's
Would it be
really big.
n plus n?
N plus n. Then what determines the n plus n?
Amount of
Actually n. N plus this one, then there is total size n. What determines the n?
the number of cuts you have on the process, the number of pages that are in the process.
That is determined by your computer system. If you are using the 16-bit processor, 32-bit processor, 64-bit processor means what? At one CPU cycle, it can process only that amount of data. Which means when you read the data from the memory, so only 16-bit will be needed. Even though we got the 32-bit, the CPU cannot process the 32-bit because CPU, one cycle, it can process the 16-bit only. So which means address format will be determined by such a processor unit. So in case of a 16-bit processor, you have a 16-bit address. So 2 to the power of 16. So M is determined by the processing unit. So that is the reason when we are using the 32-bit, sometimes it's limited by, I mentioned about the disk size, file system size. Because the size on 32-bit computer is what? 4 gigabyte. That is actually, even though you can make the bigger and bigger, but your address format is this one. So you cannot use bigger size. So same thing, on your memory, the M is determined by your processing unit. However, 64, 2 to the power of 64 is really big. So practically no limitation. That's what we are saying. Okay? So 16-bit, such as the address format used in the memory is determined by the processing unit. So this is an overview of the paging hardware. So when you see the hardware, the solution means the CPU and the memory and such hardware part already embedded this process, so your operating system doesn't have to worry about this. It's a paging hardware. So when CPU read the data from the memory, first, from the address, there are two parts, page and offset. So page is from the page table and get the location of the page frame. Okay, this is a page frame F. Then offset is the same thing, it's the location from the same page. So then we can add F plus D. That is the final physical address, and this will be returned back to the CPU like this. This is a page table. So this is an example of the logical and the physical memory. One more time, when we are saying the logical memory, this is your program. And when we are saying the physical memory, this is a really physical memory. It's a page frame. So we have a page table like this. We have the logical memory, then the divide by 512 byte, or the page size. Then we are going to map or locate the page frame. This is a frame number. Okay, here's the example. So let's say our page size is 4 byte. So which means this is a program, this is the physical memory. We have the 32 byte memory. It's really small, but we pretend. So 32 byte memory. This is a physical memory, and this is your program. Your program code is 16 byte total. You can see the 0 to 15. This is a paging approach. not contiguous. In case of contiguous, you are going to allocate entire 16 byte if you have. Otherwise, you cannot. You need to do the fragmentation. So here, so we have the page size by 4, which means we are going to divide by 4, 4, and 4. Also same thing, 4, 4. So how many page frame we can have? How many page frame?
32 divided by 4.
How many?
32 divided by 4.
Which is 8.
Which is 8. So if you answer the 32 divided by 4 on your final exam, probably give up. So it's 8. Okay? So we have 8 frames. And how many pages do we need for this program?
4.
4. And also don't forget, if we have 1 more byte, 17, like the size, how many pages do we need?
5.
5. Be careful, we have the internal fragmentation, not like the 4.1, doesn't make sense. Okay, then, what we're gonna do is we try to map. So, page on your program to the page frame. So we already allocated. Let's see the page table. So 0. 0 is this one. 1, 2, 3. So 0 is in the page. This is a page frame number. And this is a logical page number. Okay? So 0 is mapped to the 5 page frame. 5 is 0, 1, 2, 3, 4, 5. Okay, so 5 goes to here, right? So you can see the A, B, C, D is the same as the A, B, C, D, like this one more. So page number 1 of your program is mapped to the 6. 6 is here. So this is the E, F, G, H. So E, F, G, H is loaded into here. So which means you are able to calculate the between. Like for example, if I'm asking the logical address 9, what is the physical address? How can you do that? First, take a look at the page table. This is a 0, 1, 2. So 2. And also, if you do not have such a diagram, still you are able to do how? 9 divided by page number. Page size is a 4. It's gonna be 2 point something. That is the third page. 0, 1, 2. So page number is the 2. Even though I do not provide this. Okay? You can calculate. Then offset is 0, 1. So page number is 2 and offset is 1. So this is the information. Then 2 is mapped to 1. Page frame number 1. So page frame number 1 is here. Then offset is 0, 1. So 0, 1. So this is the address. So 4, 5. Physical address is the 5. However, if we do not have such a diagram, still we are able to calculate. How? So page frame 1 is multiplied by 4 page size plus offset is 1. So it's going to be 5. So we can decide the physical memory. This is a good example for the final exam. Definitely I'm going to ask the question. Okay?
Professor?
Yes.
Question.
Yes.
How does EOS determine where to allocate each page?
Allocation is not mentioned yet. Okay?
Okay.
Suppose that is allocated. And we will see how to manage. Think about we have really many pages, 3 pages and many pages. Even finding the location, like this is okay, 32K. But what if we have the 16 gigabyte, the memory?
Okay, that's a lot.
Really a lot. So even the searching, it takes the time. So we will see later. Okay, so this is a paging. Okay, So we can calculate such an internal and fragmentation and performance like that. Okay. Then this is the way to allocate. So how does the operating system allocate the page frame to the page program? It manages the free frame. It's a very similar idea as what? Your portable file system. Do you remember? Your free block is managed by the bit vector. Right? So 1 means free, 0 is being used. So our goal is to find the first one. Similarly, we are going to manage the list of the free frame. Then the first one will be allocated to the pages like that. Okay. So which means CPU operating system should know this. Where is the page table? So base register for the page table is called the PTBR. PTBR is the address of the starting of your page table, and also this is the process. There's no boundary of the memory, so we need to know the length, the limit of such a page table is the PTLR. Then one more thing. If you have the 16 gigabyte, the memory size, how many page frame divided by 512? It's really huge. So your page table will be really large. It's really big. Okay. So whenever you access the disk, you need to go to the here and read the data, calculate the page frame, takes a long time, right? So whenever we encounter problem of performance, we are able to use cache. So there's the cache of the page number, page frame number. It's called the translation look aside buffer. It's called the associative memory. Let's take a look at the example. So this is a hardware solution. So hardware provides such a lookup table. So if you have the page number P, so our goal is to find the F. So what we did before is always we are going to find the page table, then the F is read it and put over here, then calculate, and finally find the location instead. This frame number is in the cache. It can be add to cache or the F cache, so depending on the computer architecture. So it's in the cache. Then instead of going to here, we try to check the page number 1. 1 is the page frame number 10. Then we can directly go here. This is called the TLB hit. What about there's no 1 over here? Then we can go to the normal way. It's called the TLB miss. Does it make sense? Yes. This size they're much smaller than this. Okay, we don't want to keep all the page number, only frequently limited, like a 10 or 20. And we are going to manage this one. If then after we miss, this will be added to the last. Not always, depending on the algorithm. You can use LRU algorithm, least recently used algorithm, or MRU algorithm, most recently used algorithm. Depending on the algorithm, you can manage. That's such a look-aside buffer. It's a TLB. So using TLB, we can do huge benefit to speed up. We don't have to access the main memory and calculation instead of from the cache. We can find the physical address. Okay, so it's after the time's up, so I'm going to stop here. So I'm not going to evaluate this one. Instead, next class, on Monday we are going to have a class. So last class before the campus close, then it will be after the Thanksgiving, it will be online, fully. So you don't have to come to, last class will be the last one. Okay, next week, Monday. Okay, then we will cover last of the part of this one. Hopefully that we can finish the chapter 10 on time before the final exam. Okay, next week I'm going to give the more specific information about the final exam. Okay, any questions? Okay, thanks so much. Then we will see on Monday.